In this class, we are going to study how to solve heat and wave equations. Here, we make use of a method which is called as method of separation of variables. Hmm? So what we do here is, see, we consider a partial differential equation in x and y. Right. So what will be the solution? Actually, z is equal to f of x, y, some constants will be there and all. So see, this z is a function of both x and y. So here what we assume is, suppose if z is a function of product, a function of x into a function of y. That is, if I write z as a function of f x into function of y, that is z is equal to f of x into g of y, then it may be possible to separately get a differential equation in z and x and separately a differential equation in z and y. So I can get a differential equation in x and I can get a differential equation in y. So once I get a differential equation in x, you see it becomes an ordinary differential equation in x. So it is a function with one variable x. So now we know the method. Say we know how to solve first order differential equation, and we know how to solve the second order differential equation. In first order differential equation, so many methods are there: variable separable method, homogeneous equation method, exact equations method, and all. And in higher order differential equations, we have to find out auxiliary, find out the solution of auxiliary equation. We have to find out the particular integral. So complementary function plus particular integral gives the solution of second order differential equation. So like this, once I get an ordinary differential equation, I can use my earlier methods to solve those equations. That is the idea behind this method. So what I will do here, so I assume the solution as z is equal to f of x times g of y. Then I find out del z by del x, I find out del z by del y, del square z by del x squared, del square z by del y squared, then mixed derivative del z by del square z by del x del y. All those things I find out, and I substitute them in the given equation. Right. Then I'll separate the variables. That is, I bring x terms on one side, I'll bring y terms on the other side. So my left hand side function gives me the function of x, the right hand side gives me the function of y. So now I'm equating both of them. I'm equating the function of x to a function of y. So when it is possible? So it is possible only when it is both of them are equal to a constant, equal to a constant. So if I equate the right hand side is equal to a constant, I get one equation in x. If I equate the left hand side is equal to a constant, I get the other equation in y. So I can find out fx by first differential equation. I can find out gy from the second differential equation. Then fx times g of y gives me the required solution. So this is the idea behind the variable separable method. Now with this, I go to heat equation, solution of heat equation. See, I know del u by heat equation is given by del u by del t is equal to c squared times del squared u by del x squared. This c squared, it depends on the properties of the material like specific heat, then Fourier's constant, all those things. It depends on the physical or the specific properties of the material. So dou u by dou t is equal to c squared times del squared u by del x squared. So I consider this heat equation. Now this u is the heat function. So naturally it depends on the distance. That is, if I heat the rod at one end and if I measure the temperature at the other end, definitely but they differ. That means heat varies with the distance also. If I heat one rod at one end, still I can hold the rod at the other end because it is not hot. But I cannot hold the rod at the end where I have heated. So that is not possible. There the heat is more. At the other end the heat is less. That clearly indicates heat is the function of distance. Similarly, I heat the material and if I keep it just like that, then what happens? Heat dissipates. Heat dissipates the heat is dissipated to the atmosphere and the temperature decreases. After a long time, if I go and touch the material, I won't feel hot at all. That clearly indicates the heat is the function of time also. So I assume the u of xt, u is the heat. So u of x comma t is equal to capital X is a function of x into capital T, a function of t. So u is equal to x times t. Right. Now I differentiate because I need del u by del t. I need dou squared u by dou x squared. So I differentiate equation 2 with respect to t as well as with respect to x twice. So it gives me del u by del t is equal to x times t dash. Right. It is x times t dash. That is x is constant, capital X is constant for t. So del u by del t is dou by dou t of x into capital T. So capital X is constant because it is a function of x only. T will not be there. So I take that out. X times, since capital T is a function of t only, it is only a function of one variable. Therefore, it becomes the ordinary derivative instead of partial derivative. It is the total derivative, that is ordinary derivative, c d by dt. So what I get, it is x into d by dt of t, that is nothing but t dash. Though del u by del t with x times t dash. Similarly, if I differentiate u with respect to x twice, I get this one. Del squared u by del x squared is equal to t times x double dot. Right, x double dash on dot dash. So now what I will do, I use equation 3, I substitute equation 3 and equation 4, del squared u by del x squared and del u by del t in my equation. So del u by del t is x times t dash, del squared u by del x squared is t times x double dash. So I substitute those two values here in the equation 1. I get this equation, x times t dash is del u by del t is equal to c square times del squared u by del x squared is t times x double dash. So I get the equation. Now I'll try to separate the variables. I bring that c squared times t to the left hand side. Then I shift this x to the right hand side. So 1 by c squared times t dash by t is equal to x double dash by x. Right. So now if you observe here in this equation, see, if I consider this equation, that is, if I consider, say, this equation, that is t square 1 by c square t by t, so t dash by t. So this is a function of t only, function of time only. Then if I consider this one here, x double dash by x, it is a function of x only, right? So here equation 5, the left hand side is the function of t and the right hand side is a function of x. See, I have to equate both of them. Therefore, both of them will be equal to some constant. I call that as k. So I get an equation like this: 1 by c squared t dash by t is equal to x double dash by x. So that is equal to a constant of NRE, a constant k. Right. So this gives me two equations now. I can equate left hand side is equal to k. I can equate right hand side is equal to k. So here, see, I got this equation. T dash by c squared t is equal to k and x double dash by x is equal to k. So this gives me the two equations. So it is t dash, if I cross multiply, t dash is equal to k times c squared t. If I shift this k times c squared t to the left hand side, I get t dash is minus k into c squared t is equal to 0. The same thing. This x is shifted to the right hand side. So it becomes k times x. So if I shift this kx to the left hand side, x double dash minus kx is equal to 0. So that gives me equation 8. Right. Now I have to solve these two equations. So t dash is equal t dash minus k times c squared t is equal to 0. X double dash minus k times x is equal to 0. I have to solve these two equations. So now I consider all possible cases for k. K is a real number. So k can be positive or k can be negative or it can be 0. So I do not know because it is a general constant. Right, now I consider the case when k is positive. So what I will do is, since I want to make sure that k is positive, I replace this by p squared. P is a number. P is a number. Since we know that any number, if I square it, I get a positive number. So I make sure that whatever I have considered is a positive. So I square that. So I assume k to be p squared. Right. So if I replace k by p squared here, what I get dt by t, that is t dash. T dash is what? Differentiation of t with respect to t, capital T with respect to small t. D capital T by d small t minus p squared c squared of capital T is equal to 0. That is my ninth equation. D squared uh, d squared x by dx squared minus p squared times capital X is equal to 0. That is my 10th equation. So if I solve these two, see, if you look at equation 9, this is a linear differential equation of first order. That is also called as Leibniz equation. Once you know that the equation is Leibniz, what you have to do? You have to find out P. This is my P. Then integrating factor will be e raised to integral PDX. Then solution is what? Dependent variable times the integrating factor is equal to the right hand integration of right hand side times the integrating factor dx. That is my solution. So here I consider the solution of 9. So integrating factor is e power integral p dx. P is minus p squared c squared. So e raised to integral minus p squared c squared dt, that is nothing but e raised to minus p squared c squared is there constant, so times t. Therefore, what is the solution? T into integrating factor, because here the dependent variable is t, right, and independent variable is small t. So capital T times the integrating factor is equal to integration of the right hand side of this equation. Right hand side is what? Right hand side is 0. So right hand side 0 into e raised to the integrating factor dt plus the constant of integration. Clearly this is 0. The integration is 0 because the integrand is 0 there. So my solution is what? I shift this e power minus p squared c squared t to the right hand side. So I get t is equal to a into e raised to p squared c squared t. So that is my solution for t. Now what is the other one? I have to find out x. So for x, I should solve this second equation, that is 10th equation. So the equation 10 is x double dash minus p squared x is equal to 0. So I replace capital D, that is small d by dx by capital D. So I can rewrite this equation as d squared minus p squared times x is equal to 0. So d squared minus p squared is equal to 0. That gives me p and minus p as the roots. So p and minus p, they are the real and not equal roots. So my solution is what? Capital X is equal to k1 e raised to px plus k2 e raised to minus px. Therefore, the final solution, I got x, I got t. So my solution is what? U of x comma t is equal to k1 e raised to px plus k2 e raised to minus px times t is what? A into e raised to p squared c squared times t, or ux comma t is equal to k1 times a, that is I take this a inside, k1 times a I write as a1, k2 times a I write as a2. So u of x comma t will be what? a1 e raised to px plus a2 e raised to minus px times e raised to p squared c squared t. So this is my solution when k is positive. Now I go for the second case, k negative. If k is negative, that is if k is minus p squared, as I told you, let p be any number, p squared will be always positive. So negative of p squared. So that gives me a negative number. So to make sure that the number which I consider is always negative, I assume k to be minus p squared, right? So if I replace k by minus p squared in my equation, say 7. So k by minus p squared. So minus of minus p squared, that gives me plus p squared c squared. Similarly, x double dash minus of minus p squared into x, that gives me x double dash plus p squared x is equal to 0. Therefore, I get these two equations. D capital T by D small t plus P squared C squared T is equal to 0. Right. So the other equation will be what? D x double dash, that is d squared x by dx squared, minus of minus p squared will be plus t squared times capital X is equal to 0 will be my other equation. See here, if I observe, I follow the case one. So d capital T by d small t plus p squared c squared t is equal to 0 is a Leibniz equation. Therefore, capital P is p squared c squared, r is 0. So integrating factor is what? E power integral p squared c squared times dt. So solution will be what? T into e power integral p squared c squared times dt is equal to 0 times the integrating factor plus the constant of integration a. So since this integration is 0, since this integration is 0, I get the solution as what? T into e power p squared c squared small t is equal to a, or capital T is equal to, I shift this e power p squared c squared t to the right hand side. So what I get? Capital T is equal to a times e power minus p squared c squared times t. Right. So I got the solution for t now. Now I find out the solution for x. That is, I have to consider this equation x double dash plus p squared x is equal to 0, because the equation was x double dash minus this equation minus k times x is equal to 0. Here I replace x by minus p squared. So I get the equation as x double dash plus p squared x is equal to 0. Again, the usual. What you have to do? D squared capital X by D small x squared plus p squared capital X is equal to 0. Put d by dx is equal to capital D squared by dx squared will be capital D squared. So if I substitute those here, make use of that notation, I get d squared capital D squared plus p squared of x is equal to 0. So definitely d squared plus m squared plus p squared is equal to 0 gives m squared is equal to minus p squared. Square of a number negative, so it is imaginary. So what I get? The roots as plus I times p minus I times p. So the roots are complex numbers. So accordingly, what is the solution? X is equal to C1 cos px plus C2 sin px. Therefore, what is the final solution? X times t gives me the final solution. So u x times x comma t is equal to C1 cos px plus C2 sin px into a times e raised to minus p squared c squared times t. Right. So if I again as in the earlier case, a times c1 I write as a1, a times c2 I write as a2. Therefore, my solution will be what? U of x comma t is equal to a1 cos px plus a2 sin px times e power minus p squared c squared t. So this is my second solution, that is equation, a solution of the heat equation when k is negative. Then I go to the third case when k is 0. So if I consider a constant, either it can be 0 if it is a real number, either it can be 0 or it can be positive or it can be negative. So I consider two cases. One is positive k case, the other is negative k case. Now I consider the third case, k is equal to 0. So if I consider k is equal to 0, what are the equations now? My equations, see, I go for this one now. T dash minus 0 times c squared t is equal to 0. That means t dash is equal to 0 is my first equation. Then the second equation will be what? X double dash minus 0 times x is equal to 0. So that will be my second equation. That means x double dash, because this becomes 0 when k is 0. Similarly, this becomes 0 when k is 0. So I get my two equations when k is equal to 0 as d capital T by d of small t is equal to 0. Then d squared x by dx squared is equal to 0. So these are the two equations. So now what is the solution now? The solution is d capital T by dt is equal to 0 means what? The solution t must be a constant. Right? T must be a constant. That's all. So if I differentiate t with respect to small t, I get back 0. So t must be a constant. That is my first equation. And d squared x by dx squared is equal to 0. That gives me the solution as capital X is equal to A1X times B. So capital U, that is therefore U of X comma T will be what? Capital X into capital T, that is A1X plus B times A. If I replace A1 by A1, AB by A2, Ux comma T will be what? A1X plus A2, right? So this is my third case. So when K is equal to 0, it is A1X plus A2. When K is negative, it is A1 cos px plus A2 sin px times e power minus p square t. Then when K is positive, the solution is what? A1 e raised to px plus A2 e raised to minus px times e raised to p squared c squared t. So these are the three solutions depending on k is equal to 0. Now let us discuss what will be the exact or which solution suits our heat equation, right? Now what are the physical properties of heat? You know, keep if I heat a substance and if I keep it after a very long time, the heat reduces, that is, it will be decreasing as temperature, as time increases, the heat decreases, right? So that is my first observation. The second observation is heat is a function of distance also, that we have told, right? We have observed. So if I consider, or if I take a rod and if I heat it at one end and if I hold it at the other end, it will be less compared to the heat at the other end. Why? Because I am heating at that point. That clearly indicates if I go far away from the heat, so the temperature reduces. That is, heat becomes lesser and lesser as the distance increases. That means, again, as X increases, the heat decreases. So these two are the physical observations. What are those two observations? One is what? As the time increases, the heat decreases. As T increases, you should decrease. That is first observation, because U is the heat function, right? And as X increases, then also U should decrease as the temperature flows from higher concentration to the lower concentration, high temperature to the low temperature. That clearly indicates if I measure the heat at far off places, it will be less. That means as X increases, T, that is the heat temperature, decreases. So these two are my observations. Now I consider the first case. That is, we know that when K is positive, I get an equation like this: Ux comma T is A1 e raised to Px plus A2 e raised to minus Px into e raised to P squared C squared T. Right? So what this will be? If you observe, as X increases, what happens? So e raised to Px is 2.306 raised to some P times X. So as X increases, since the base is greater than 1, right, this is an increasing function. That means as X increases, this also increases. And I consider this one. So first function is, it is adding, that is, it is increasing. Second function, if you observe, see, as X increases, since it is minus, see, it will be a positive function only. E raised to minus Px will be positive, but it goes on decreasing because E is 2.3 something. So e raised to minus P times X, right? As X increases, it is like e raised to minus infinity tends to 0. It starts from higher values, it starts reducing, but always it is a positive. So you have got an increasing function e raised to Px, plus you are adding something. So in total, this function, what? This function is an increasing function. So that clearly indicates as X increases, the total value increases. But whereas in physical situations, in heating the rod case, as X increases, the temperature should decrease. But the first solution gives me what? The first solution gives me as X increases, or says me uh, as X increases, the temperature increases. Therefore, definitely this is not an equation which I want, because it won't satisfy my requirement. My requirement is what? My requirement is like as x increases, u should be a decreasing function. Similarly, if you consider e power p squared c squared t, p squared c squared, they are positive quantities. Now, e raised to anything positive, as t increases, definitely e raised to p squared c squared t also increases. That means what? Yes, p increases, u also increases, but in heat case, as temperature, as t, the time increases, heat should decrease. Therefore, for both of these reasons, right, for both of these reasons, one, the first case, when k is positive, I am having no doubt this is a solution. If I differentiate it with respect to t once, and if I differentiate it with respect to x twice, and if I add that in the equation, definitely that heat equation is satisfied, but it won't satisfy the physical conditions. Therefore, this equation cannot be a solution of heat equation. If I don't treat that as heat equation, then that equation, this solution, this K positive case may be true, but for heat equation, it is not true. It cannot satisfy the conditions. Then similarly, I consider the third solution, that is when K is equal to 0 case. Ux comma T is what? A1x plus A2, it is independent of T. Independent of t means even if I go at t is equal to infinity, that is even if I heat a substance and I keep it aside, even if I go after half an hour and if I touch it, the temperature won't change at all. It is independent of time, it says. So it is, which is not true. So it cannot be solution as far as time is concerned. Then I come to x case. So what this function says, a1x plus a2. So definitely as x increases, a1x plus a2 also increases, right? Once it is increases, uxt becomes an increasing function for x also. But it is not true. If I go far away from the heat, definitely heat is reducing, right? Therefore, that equation, third equation also cannot be the solution of heat equation, even though it satisfies the heat equation. Now I consider the second solution when k is negative case. So if k is negative, what happens? A1 cos px plus A2 sin px. See, cos px and sin px, they are the trigonometric functions, and always they lie between +1 and -1, because sin x cos x, they vary between -1 and +1. Therefore, in total, whatever is the value of x, even if I go far off places and all, it will be a finite quantity. A1 cos px plus A2 sin px will be a finite quantity, as cos px and sin px, they lie between -1 to +1. So the first product, the first case, that is first bracket, a1 cos px plus a2 sin px, it is a finite value, right? Then I consider the second equation, second function, e power minus p squared times t. So as time progresses, what happens? It will be a decreasing function, e power minus of this. Finally, when t goes to infinity, it is e power minus infinity. T will be 0. Finally, it becomes 0. So that's what is the case in case of heat. So if I heat the heater rod and keep it aside, and if I go after a long time and touch it, definitely temperature will not be there. It is dissipated to the atmosphere, right? So therefore the second solution when k is negative case will be an appropriate solution for the heat equation. Therefore, my solution for heat equation will be u of x comma t is equal to a times cos px plus b times sin px into e power minus p squared c squared t. So this will be the solution of heat equation. So in the next lecture, we are going to solve the wave equation also in the same way, in the similar fashion, that is by the method of separation of variables. So what we do, we consider the solution as a product of a function of t into a function of x. Then I find out the derivatives, required derivatives. In case of wave equation, I need del squared u by del t squared, and I need del squared u by del x squared. So I find out these two values, I substitute in the given equation, then I separate the variables as I did here, then I get the two differential equations, ordinary differential equations, and I solve them. Then I multiply them. I find out the product to get my solution of wave equation. So that we can discuss in the next class.